Hello, in this video we're going to look at sandwiching sequences of real numbers. Really our main theorem will be bullet point number 5, which is the sandwich theorem for sequences of real numbers. And we're going to build up to that. So number 1, we're going to assume that a sequence converges to A and all the terms are greater than or equal to 0, non-negative, and that's for all n. And we want to show that the limit has to be non-negative. And the proof is by contradiction. We're going to suppose that the limit is negative, and then show that this contradicts our assumptions, and therefore A must be non-negative. So let's let epsilon be positive, but less than this positive number. Remember, we're assuming that A is negative, so minus A is actually positive over 2. Then we need to find an n such that little n being greater than capital N, we have this condition that it's they're really close. But this condition implies this. So remember, if you take away the absolute value, then you have to put a minus epsilon less than this less than epsilon. But then we can add A to everywhere and we get this. But note here, A is a negative number, and we're adding a small positive number that's smaller than negative A. So this remains negative. So note that A plus epsilon is negative. But this violates our assumption that all our terms are positive. So since if A is the limit, then we should be able to find a capital N that meets this requirement, but it's not possible because AN are positive and all of these are negative. So it violates the assumption that each term is positive, and therefore the limit must be non-negative. Done. So now the second proof here is assume that we have a sequence AN that converges to A, and that each term is less than or equal to some number K. This is for all n. We want to show that the limit of this sequence has to be less than or equal to K. Now, we define a new sequence, Bn, which is K minus An. Now note that Bn is positive for every term, and that the limit of this sequence is actually K minus A, because the limit of, these are two actually converging sequences. Of course, this converges to itself, and then this converges to A, so the Bn converges to K minus A. Now, by property 1, we know that this has to be greater than or equal to 0. But this implies that A is less than or equal to K. And then we're done, because that's what we wanted to show. Now, if AN is a convergent sequence to A, and BN is a convergent sequence to B, and AN is less than or equal to BN for every term, we want to show that the limit, that A is less than or equal to B. So the proof is we develop a new sequence, Cn, which is Bn minus A. And note that Cn is non-negative, and the limit of Cn exists, and it's B minus A. Then by property 1, B minus A must be positive, which implies A is less than or equal to B. Now this next property or theorem has a name. They call it the sandwich theorem for null sequences. So let's assume A, N, and Bn are sequences with this property. They're all non-negative, and Bn is always greater or equal to An. This is for all n. And Bn converges to 0. Then the sequence AN also converges to 0. So you can kind of see that it's being pinched down to 0. So the proof is this: since we know that Bn converges to 0, and this is kind of shorthand notation. You go, given epsilon greater than 0, there exists a capital N such that n is greater, that when n is greater than capital N, then this condition's met. That Bn, the absolute value of Bn is always less than epsilon. So that's the definition of convergence to 0. And actually, here's a side note, not part of the original one, that if Bn converges to 0, look at the absolute value of Bn converges to 0. We get it by default. Okay, that's a side topic. So then this condition is this, that Bn is between these two numbers, and that's for all n greater than n. But by assumption, we know that An is less than or equal to Bn, right? And that's for all n. And it's positive, so it's always greater than this negative number. Now, if we take away the Bn, we get this. And that's for all n. But that's saying that the absolute value of An is less than epsilon for all n, greater than big N. Well, that implies that An converges to 0. Now, the main result for this theorem, or this video, is the sandwich theorem for sequences. And that's if we have 3 sequences with this inequality, An less than Bn less than Cn, and that's for all n. And we know that An converges to R and Cn converges to R, then Bn also converges to R. So let's a note here that the sequence Cn minus An, because they're both convergent sequences, we know that that's equivalent to the difference of these sequences, which converges to R minus R, which is 0. So this sequence converges to 0. Now, by assumption, Bn minus A is a little bit smaller than Cn minus A. And since they can all be equal, that needs to be a greater than something. Now, by property 4, the sandwich theorem for null spaces, because we fit into that we showed that this converges to 0. So this sequence converges to 0. Okay. Now, we don't know anything about An yet. I guess technically we know that it converges, otherwise this would blow up. And maybe we do or don't, I'm not sure, I'd have to think about that. I meant Bn. We know An converges. But Bn, the sequence Bn, can be thought of this sequence, Bn minus An plus An. Now, we know that this sequence converges to 0. We just showed it by the sandwich theorem for null spaces. And we know this is a convergent sequence. So we have the addition of 2 convergent sequences, so it can be thought of like this. And then these converge to the individual limits, which this converges to 0, and this converges to R, which is equal to R. So the series Bn, sequence Bn converges to R, and we're finished. Well, that's all I have for today. Hopefully you enjoyed that. I sure did. Going through these videos makes me want to pull out my topology book and my real analysis book, dust them off, and really get into detail. But I'm kind of trying to stay on topics that I think statisticians would like. Well, anyway, like the video and subscribe so you don't miss the next one. Thanks. Bye.